Welcome back to Mr. Angelo's awesome geometry class. We're getting into the second to last chapter of the whole year, exploring solids. So we're going to focus on finding surface area and volume of three-dimensional shapes. So let's go ahead and define all of these three-dimensional shapes and some of the vocabulary we'll be using. So a polyhedron is a three-dimensional figure whose faces are polygons. So an edge, this red part right here, is one of the sides of the polygons. Right? One of the sides of the polygons. The face is the actual polygon itself. So it's colored in with, how about this? And a vertex is where three or more edges come together. So our vertex, there, and then there's one in the back, way back there too. Right? This one has 2, 4, 6, 8 vertexes, or vertices. So let's see which ones are polyhedrons. So remember what it means to be a polygon. Are circles polygons? No, right? A polygon is a closed figure with no curves, all straight line segments. So is this a polyhedron? Yes. Yes. No? No? Yes. So cylinders and spheres are not polyhedrons, but we will go ahead and investigate the surface area and volume of each of those. So we're going to look at more than just polyhedrons. We'll look at solids in general. So the name for this is a triangular prism. This one we call a cylinder. This one is a sphere. And this one is a pyramid. If not, then we'll come up with names and definitions for all of these. All right. Regular versus convex. We know that what regular means for a polygon, all internal angles are congruent and all sides are congruent. A regular polyhedron, all faces are regular polygons. The easiest one that comes to mind is the cube. Right? All the faces are squares. And then let's do convex versus concave. Convex versus concave. So convex, any face, if extended, does not cut through the polyhedron. So if I extend the face, it wouldn't slice off a piece. Concave is just the opposite of that. So concave not convex. So this polyhedron over here, is it concave or convex? Concave. Concave, right? If I went and extended this side right here, it would cut through there. So this is concave. Moving right along. So a cross section is the intersection of a solid and a plane. Remember, a plane is like you're a piece of paper going on and on in all directions, right? And if I sliced it, so think of it if you're taking a knife and chopping an orange, if you will, and just looking at the shape it creates. Okay? Let's look and see. So if I did chop that orange in half and held it up, what shape would I have? It's a circle. So the cross section would be a circle here. What about the cross section of the cube? Square. And then what about if I slice the corner off of a cube? What shape do you think that's going to make? You're going to take off a pyramid, but the cross section is just the shape if you're looking at it. So it's going to end up being a triangle. All right. Now we're going to look at Euler's theorem. Platonic solids. So let's go ahead and count the number of faces in a tetrahedron. So we're going to have 4 faces. How many vertices? 1, 2, 3, 4. And then how many faces? Or how many edges, my bad. We had 4 faces. How many edges? So let's go ahead and count these. 1, 2, 3, 4, 5, 6. Try the cube and the regular octahedron, and then we'll look at these last 2 together. See if you can count the number of faces, vertices, and edges for those. So take a second to do that. All right, so our cube, we know a cube has 6 faces, like a normal dihedral. And then how many vertices? 1, 2, 3, 4, 5, 6, 7, 8. And then how many edges? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Yeah. So we're starting to get a pattern. And off the hedron, we have 8 faces. How many vertices? 6 vertices. And then 12 edges. So it turns out there's this pattern. And it's called Euler's theorem. The number of faces plus the number of vertices equals the number of edges plus 2. So a dodecahedron has 12 sides. It has 20 vertices. So how many edges does it have?
34.
So this is 32, and then we're going to subtract 2. No, it's edges plus 2, so 30 plus 2 equals these 2. Okay? So the number of edges plus 2 equals the sum of the faces and the vertices. So if I had 20 here, and let's say I had 30 here, can I figure out the number that goes here?
10.
Well, very good. Well, right? 20 plus 12, 32. 30 plus 2, 32. All right, so let's go ahead and use that Euler's theorem to see if you can figure out example 3. So figure out example 3. All right, here we go. So F plus V equals E plus 2. So I'm given F is 5. I'm looking for V. I have 9 edges. Fairly simple to solve. So this is 11. So 5 plus V equals 11. Subtract 5 from both sides. Vertices equals 6. 5 plus 6 is 11. 9 plus 2 is 11. Right? So it equals. And again, over here, F plus V equals edges plus 2. So now I'm given faces, 20, vertices, 12, edges plus 2. So I end up with 32 equals E plus 2. Number of edges, 30. Solve these. And for all of you that love soccer. So a soccer ball is made up of 20 regular hexagons and 12 regular pentagons. How many vertices does it have? All right, so let's go ahead and use this. So F plus V equals E plus 2. I want to solve for that vertices. So I need to figure out how many faces and edges it has. So faces is easy, right? We have 20 hexagons plus 12 pentagons. So the number of faces we have is 32. All right. So on this side, we're going to have 32 plus V equals. Now we need to figure out the number of edges. Right? So that's not as difficult as it seems. Each pentagon has, well, let's start with hexagons. Each of the 20 hexagons has 6 sides, right? Because they're a hexagon. And then each of the pentagons have 5 sides, and there's 12 of those. But if you're looking at the soccer ball, right? Notice here that each of the edges shares an edge with another one. So what we have to do is cut this in half. Okay? Cut that in half. Since each edge shares another one, we don't want to double count. That's the number of edges. And I get a total of 90 edges. And now we can use Euler's theorem. Plug that in. So we get 32 plus V equals 92. Subtract 32 from both sides. How many vertices does it have? 60. So that is 11.1. Looking at some definitions and Euler's theorem.